So next, depending on the Fresnel's assumption with regards to the diffraction pattern which are observed when the both this source and the screen are at finite distance from the obstacle or the aperture, we will discuss Fresnel's half period zones. Okay, so this Fresnel's half period zones is constructed to explain the Fresnel type of diffraction patterns that are observed and how they are formed. Okay, and it also helps us to explain the rectilinear propagation of light based on the wave theory. Till now we know that according to ray optics that light rays always travel in straight line, they never bend their path, but if we consider the wave theory of light, then we observe that there is the phenomenon of diffraction where there is the bending of light under some particular circumstances, okay, which is of course in contrast or is not in agreement with the rectilinear propagation of light. Okay, so but this construction will help us to sort that matter out. Okay, so first of all, what we have to do, we have to construct construct this half period zones. Like one of the Fresnel's assumptions were that any wavefront can be divided into small element or zones known as Fresnel zones. Okay, so first we will construct such zones. Okay, so to do that, what we'll do, we will consider a plane wavefront. So suppose first of all, suppose we have this parallel beam of light propagating through the medium. Okay, we are showing just some lines, parallel beam of light propagating through the medium. Then if we want to draw the wavefront corresponding to this parallel beam of light, then of course the wavefront will be a plane wavefront. Okay, so here now we are drawing such a plane wavefront. Okay, this is the plane wavefront and this parallel beam of light is propagating in this direction. Okay, so suppose this plane wavefront, we name it as A, B, C, D. Okay, so now what we want to do, now as the beam of light is propagating, suppose we take any point in front of this wavefront. Okay, and we want to find what will be the effect of this parallel beam of light, or suppose this wavefront effect at O due to this wavefront ABCD. Okay, so to find that, first of all, what we have to do, we have to divide this whole wavefront ABCD into small element or zones. Okay, so the resultant effect basically means that what is the intensity or amplitude at the at point O due to this wavefront ABCD. Now, according to Huygens principle, we know that every point on this wavefront are in same phase. Okay, so all the points on the wavefront ABCD are in same phase. Okay, now so that every point on this wavefront will act like that is according to Huygens principle, that act like is a point source of secondary wavelets, which will generate secondary waves, and those waves will travel in every direction. Okay, so when they expand in space and travel in every direction, all the waves at some point will reach point 2, and thus will get the resultant effect, or which is the resultant intensity or resultant amplitude at O. Okay, so if a resultant effect means what is the amplitude or intensity. We have to find that point O in front of this wavefront ABCD. So to find that resultant effect, what we'll do, we will draw a perpendicular from O on this wavefront AB. Okay, so suppose we draw this perpendicular. Okay, and over here suppose this point is P. Okay, and point P is called the pole. Okay, and suppose this PO or OP is equals to B. Okay, so this distance is equal to B. So now what we'll do, we will draw a sphere, okay, taking O as center. Okay, so first draw a sphere with O as center. And what will be the radius? Radius will be this B plus lambda by 2. Okay, so we'll draw a sphere. We have to imagine that we are drawing a sphere with O as center and radius B plus lambda by 2. Okay, so that length will be slightly greater than this B. And what is lambda? Lambda is the wavelength of this light we have employed. So if we do so, then what will happen? So if you draw as imagine a sphere, okay, in 3D, so what will happen? It will cut a portion because that radius will be greater than OP. So the radius B plus lambda by 2 will be greater than OP. So what will happen? That sphere will cut the wavefront ABCD. Okay, because the radius suppose will be this much. So if we draw a sphere, the wavefront ABCD will cut this sphere. Okay, so it will be, the situation will be somewhat like this. So suppose this is our sphere. Okay, then there is this wavefront ABCD which will cut this sphere. Okay, in this by a circle. Okay, so this much. Okay, so if we draw it again, suppose this is the sphere. Okay, and here is the wavefront ABCD. Okay, then it will cut a circle. So it will basically will be a circle. This much, this will be the circle. So this much is B, but this much length, the radius is B plus lambda by 2. Okay, it will cut a circle. Okay, so if we draw a sphere, okay, with the radius B plus lambda by 2, it will cut a circle on the wavefront ABCD. Okay, and what will be the radius? Suppose that over here we are showing only that circle. So suppose this will be the circle, and suppose so this much again will be the radius. As you can see that this is the radius, it will be B plus lambda by 2. So if we join these two lines, we will get the radius of this sphere, okay, which is B plus lambda by 2. Okay, and suppose this is PM1. Okay, so the radius of the circle, radius of the circle is PM1, which is PM1. Okay, so in this way what we can do, we can draw more circles, okay, concentric spheres. Okay, so we can draw more concentric spheres, okay, which will cut even more circles with the on the wavefront ABCD. Okay, more concentric spheres means all the spheres will have the same center at O. Okay, and those circle and more concentric spheres. Okay, and the first one had, if you remember, the radius was b plus lambda by 2. Then the radius will be b plus 2 into lambda by 2, and the circle will have and it will cut a circle on the wave front ABCD, and the circle will have a radius PM2. Okay, then again the next the bigger one will be b plus 3 into lambda by 2, and it will cut the wave front with a radius PM3. Okay, then the concentric sphere will have a radius of b plus 4 into lambda by 2. Then again this sphere will cut the wave front in a circle. Okay, and the radius of that circle will be PM4 in such way. So in this way, if we draw the nth sphere, okay, so this is the first sphere, this is the second sphere, this is the third sphere, this, and then it will be the nth sphere, and in this case it will be the second circle, it will be the third circle, it will be the fourth circle. In this way, for the nth sphere we get the radius to be b plus n into lambda by 2. So the circle, it will cut the wave front into, will have a radius of pmn, and it will be the nth circle. So in this way, so here in this way, if we do so, we will divide this wave front A, B, C, D into different zones. You see, so this PM1, the first circle is the PM1, which the M1 circle you can say, okay, which has a radius of PM1. Okay, so this OP is equal to B, and then if we joined O and M1, we got the radius of this first concentric sphere, which has a radius of b plus lambda by 2. Then we get a bigger, then we draw a bigger concentric sphere with a radius b plus 2 into lambda by 2, which will cut the wave front into this second sphere, this empty sphere. Okay, this second one with the radius PM2. Then the next bigger one, a bigger sphere, will have a radius of b plus 3 lambda by 2. Again that sphere will cut the wave front into this third circle M3. Okay, which has a radius of PM3. In this way, for the nth concentric sphere, we get the radius to be b plus n into lambda by 2, and the and it will cut the wave front in this circle, the mn circle, with the radius pmn. Okay, so in this way, you see, as we do this construction, we have divided this wavefront ABCD into different zones. So the first zone you can say is the circular zone. Then we have some circular concentric rings or annular zones.